Hi, I'm Garrett Wong. I play the part of Ensign Harry Kim on Star Trek Voyager. On my show, Voyager and its crew travel to distant stars, planets, and galaxies. Of course, when NASA scientists navigate spacecraft through our solar system, it's a little more complicated than just punching coordinates into a computer. On this episode of NASA Connect, NASA scientists will show you how they use math, like geometry, to launch spacecraft to Mars, and how geometric shapes contribute to the exploration of the Red Planet. So, fasten your seatbelts as hosts Jennifer Pulley and Van Hughes navigate you at warp speed through another exciting episode of NASA Connect.
Welcome to NASA Connect, the show that connects you to the world of math, science, technology, and NASA. I'm Jennifer Pulley.
And I'm Van Hughes. We're here at the Virginia Air and Space Center, located in Hampton, Virginia.
Get a load of all the cool exhibits they have here. There's an Apollo spacecraft that took astronauts to the moon. They have models of mini rockets since spaceflight began. And behind us, this is an exact replica of the Viking spacecraft that landed on Mars in 1976. I was just a kid then.
So, how did NASA get from the Earth to the fourth planet from the Sun? Now, obviously there are no roads or signs in space. Is the path a straight line?
Or is it a curve? On today's NASA Connect, we'll learn how engineers and scientists use a branch of mathematics called geometry to navigate a spacecraft to Mars. We'll also learn about the role that circles, angles, and ellipses play in the exploration of Mars. We'll talk with researchers at NASA's Jet Propulsion Laboratory in Pasadena, California, and NASA Langley in Hampton, Virginia, who are all working on that very thing. We'll explore past, present, and future missions to Mars and see how geometry is used to get us there.
Plus, we'll explore the age-old question, is there life on Mars? Later in the show, we'll be joined by students from Bridge Street Middle School in Wheeling, West Virginia. NASA Connect asked them to conduct a geometry activity using ellipses and circles. They'll share their data with you so you can repeat the activity and obtain your own results.
Plus, we'll go on location with NASA's Educational Technology Program Manager, Dr. Shelley Canright, who is with some students in Virginia Beach, Virginia. These students are using the internet to conduct a web quest on the future colonization of Mars. We'll also learn how intelligent spacecraft are being developed to explore Mars in the Mars Millennium Project. Stay tuned to learn more about this awesome project.
And to stimulate your brain, every time Norbert appears with a cue card, that's your cue to think about answers to the questions he gives you. Got it?
So, are you ready? Let's go get the story angle on the world of geometry.
Who was Pythagoras, and what did he contribute to geometry?
Explain how geometry is used in your everyday life.
The word geometry comes from two Greek words, geo, which means the earth, and metron, which means to measure. Today, geometry is more the study of shapes than it is the study of the earth. Basically, geometry is the branch of mathematics that deals with the position, the size, and the shape of figures.
One of the greatest mathematicians was an ancient Greek named Pythagoras. He discovered some of the most important mathematical concepts that came to be called geometry.
One observation he made was that gravity is vertical, or 90 degrees to the horizon. From this observation, Pythagoras discovered that the 90-degree angles from 4 right-sided triangles make up a square. Watch this. If I have one right angle, and I place 3 other right angles around it, like this, I eventually wind up with, ta-da, a square. That's pretty neat. Let's do the math. Knowing what Pythagoras discovered about the right angle, can you calculate how many degrees are in this square? If you multiply 90 degrees times 4, you're right, This square has 360 degrees. What other shape has 360 degrees?
A circle. You know, Pythagoras proved that there are relationships between different geometric shapes. What relationships can you see between other geometric shapes?
Get this. Pythagoras found out even more laws about the right triangle. If we look at the same square, but just a little differently, we can see that half the area of this square equals a right triangle. Now, how can we use math to calculate the remaining angles of a right triangle? Simple. Squares are 360 degrees, we know this. If we divide it in half, this triangle must equal 180 degrees. Now, we know this is a right triangle. This equals 90 degrees. If we subtract that from 180, we get 90 degrees. These two angles must add up to 90 degrees. This is true for every right triangle. It's true for this right triangle. It's true for this right triangle. And it's even true for right triangles that look like this. In order to calculate the remaining angles of a right triangle, you have to use math and geometry.
Geometry is used in everything we do, from constructing roads and buildings to playing football or pool. Okay, here's the big play. It's you and me, okay? I'll toss the big pass to you, you go down and out. Got it? Got it! Great! Now, let's see. If I toss the ball directly to Jennifer and don't anticipate where she'll be, I'll miss her completely. However, if I know she's cutting right and I throw the ball at the correct angle, I should get the ball to her. Hey! My perfect pass just created a right triangle. Geometry is everywhere.
Hey, way to go, man! Without geometry, it would be impossible to organize precise patterns and play a simple game of football. My friend Lynn Chappell is an 8th grade math teacher at Huntington Middle School in Newport News, Virginia. Let's see what information she has about Pythagoras and geometry.
The most important discovery that Pythagoras made was the relationship between the longest side of a right triangle and the two shorter sides. The longest side of the right triangle is called the hypotenuse. Now remember, the Pythagoras' theorem is a squared plus b squared equals c squared.
Now, who could tell me what that means? Charmaine.
The sum of the squares of the two shorter sides, a plus b, equals the square of the longest side, c, which is the hypotenuse.
Good answer. Now we're going to mark the right triangle that we have on this paper, and the shorter sides, also called the legs, are a and b. And the longest side is c. And remember, we call that the hypotenuse. Now what Pythagoras did was draw a square on the side of a. And remember that a square is a number times itself, a times a. And he drew a square on the side of b times b, and he drew a square on the side of c times c. But what we're going to do is we're going to cut a squared off of the side, and then we're going to cut b squared and make them fit into c squared to prove that Pythagoras was right. First, take your straight edge, and we're going to draw some parts of b so that we can cut it and it will fit. Coming along the side of c, come straight down through b squared till you touch the edge. Now connect the lower corner of b to the bottom edge of a squared. This will form a perpendicular line. Now take your scissors and cut out a squared in one piece and b squared in the pieces that you've cut it into. And then we'll fit it all onto c squared to prove that Pythagoras was right. Well, have all of you fit your pieces together? Yes. Then I guess Pythagoras was right.
And you know, Pythagoras also believed or postulated that the shortest distance between 2 points is a straight line.
Well, how come if you throw a ball from point A to point B, then it curves or arcs?
Well, Van, that's rather very simple. Ever heard of something called gravity?
Yeah, I heard of gravity! In 1600, Johannes Kepler, a famous astronomer, proved that the planets orbited the sun in an ellipse. That's another geometric shape. If you take a circle and squash it a bit, you get an ellipse. Like our football example, if we want to navigate from Earth to Mars, we have to take into account where Mars will be within its elliptical orbit.
What information did scientists first discover about Mars?
Humans have known of Mars since before recorded history. In 1609, a man by the name of Galileo first viewed Mars through his newly invented telescope. Although his telescope was no better than a modern toy, it revealed enough to prove that Mars was a large sphere, a world shaped like the Earth. Could this other world be inhabited?
Besides using the telescope, how else did scientists collect information on Mars?
Let me tell you, NASA's Mariner 4 was the first spacecraft to take close-up pictures of the red planet. As it flew past Mars in 1965, it showed a heavily cratered surface. 6 years later, in 1971, Mariner 9 arrived at Mars and became the first artificial object ever to orbit another planet. Mariner 9 saw the Valles Marineris, a canyon that stretches 4,500 kilometers, or 2,800 miles, across the face of Mars. It is so long that, if it were on Earth, it would stretch all the way from Los Angeles, California to New York, New York. All these discoveries by Mariner were seen from above the surface of Mars. What we really needed was a view from the Martian surface.
How do NASA scientists use geometry to navigate spacecraft from Earth to Mars?
Explain the goals and accomplishments of NASA's Viking mission.
All right, guys, I want you to meet Dr. Israel Tabak. He was one of the engineers who worked on Project Viking, NASA's mission to Mars, which landed 2 spacecraft on its surface in 1976.
Dr. Tabak, since we've been talking about geometry, can you tell me how geometry was used to get the Viking to Mars?
Oh yeah, it's really relatively simple. You know, most orbits around the sun are fairly circular. So if we start from Earth, for example, and want to go to Mars, we use what's called a Hohmann transfer, which is an ellipse, which takes us from the Earth's orbit out to the Mars orbit, and we meet Mars when it gets there.
So if you shot directly at Mars, it wouldn't get there.
No, it'd go to the sun and heat up too much.
And that's the most efficient way to get there.
Yes, it is.
Less money, less time.
Smaller booster.
So Dr. Tabak, let us get this straight. Circles, ellipses, angles, geometry really helps with the navigation of spacecraft to Mars like the Viking.
All very essential.
Here's an experiment you can try at home with a responsible adult that will show you how curves and angles affect the path of a projectile. Have you ever tried to aim a dart at a dartboard? Pretend the dart is a rocket and the dartboard is Mars. Now, there are 2 variables that affect the results of this activity. If you throw the dart in a straight line at an angle of 0 degrees, gravity will curve the path downward, away from the dartboard, and you miss. But if you aim a little higher for the dartboard, or at an increased angle, you should hit the target. So, if the angle is one of the variables that affects this experiment, what do you think the second variable is? If you guessed speed, or how fast I throw the dart is the other variable, then you're right. The combination of speed and an increased angle determines whether or not I hit Mars. The dartboard.
What did the Viking mission accomplish?
Well, the Viking mission really consisted of 4 spacecraft, 2 orbiters and 2 landers. Viking was the first spacecraft to land on the surface of Mars, and we got some samples from the surface and found that the samples were all oxides, mostly of iron, and that's why Mars is so red, rust.
Now, how long did this mission last?
Well, we guaranteed it for 90 days, but it lasted for 6 years.
Well, it looks like Mars is a pretty cool place.
Yeah, it really is.
Dr. Tabak, thank you so much.
You're welcome.
We really appreciate you helping us understand how you use geometry to navigate to Mars. Speaking of navigation, NASA Connect took a trip to Bridge Street Middle School in Wheeling, West Virginia. to see how students there are using geometry to understand the orbits of planets. Ready for blast-off!
Hi, we're from Bridge Street Middle School in Wheeling, West Virginia.
NASA Connect asks us to show you the student activity for this program.
When you think of the Earth or Mars orbiting a planet, you might think that the orbit is in the shape of a circle. It's really in the shape of a squash circle or an ellipse. The German mathematician and astronomer Johannes Kepler discovered this fact a long time ago. In this activity, you'll use measurement and observation to understand the meaning of the eccentricity of an ellipse. You'll calculate the distance between Earth and Mars, determine the lengths of their orbits, and learn about their orbital rates as compared to their distances from the Sun. But before we get started, here are the materials you'll need. A computer with a spreadsheet program or calculators, centimeter graph paper, 2 push pins for each group, a string 25 centimeters long for each group, cardboard, and 1 metric ruler for each group. Kepler stated that the orbit of Mars or of any planet is an ellipse with the Sun at one focus. The other focus is an imaginary point. There is nothing there. During part of its orbit around the Sun, Mars is closer to the Sun than it is at other times. This relationship can be seen in solar system data charts that show the maximum and minimum distances from the Sun to each planet. Astronomers often use the average or mean distance from the Sun instead of the minimum or maximum. Enter the data from the chart into a spreadsheet program or use a calculator, and for each planet, find the mean distance from the Sun. Now make a sketch of the orbits of the Earth and Mars around the Sun. Another column of data on the planet chart lists the eccentricity of each planet's orbit. Eccentricity gives an indication of the roundness or squashness of each ellipse. To understand what this number means, here's an experiment to do with your team. On a piece of centimeter graph paper, draw 2 lines, one near the middle vertically and one near the middle horizontally. The lines intersect at the center point. Measure and cut a piece of string about 25 centimeters long. Tie a knot near the ends of the string to form a loop. Place the graph paper on a piece of cardboard. Then place 2 push pins along the horizontal line, each 1 centimeter from the center point. These pins represent the foci. At this point, the foci are 2 centimeters apart. Loop the string around the push pins, then use a pencil to keep the string tight and draw an ellipse. Measure in centimeters the length of the ellipse along its major axis. Record the distance between the 2 foci and the length of the major axis on a chart. Then divide the distance between the foci by the length of the major axis and record the quotient on the chart. Now repeat these steps using the following distances between foci: 3 centimeters, 4 centimeters, 5 centimeters. Choose your own distance. After you have recorded the distances between the foci and the length of the major axis on the data chart, use a calculator to divide the distance by the major axis length. The quotient will give you the eccentricity for the ellipses. Remember, the value of the eccentricity should be a decimal with a value of less than 1. On the chart, make sketches of the ellipses you've created.
Analyze your data, guys. This would be a great time to stop the video and consider the following questions. How does the distance between the foci affect the shape of the ellipse? What is the relationship between the value of the eccentricity and the roundness or squashedness of the ellipse? Although the orbits of both Earth and Mars are ellipses, these orbits are close enough to being circles that we can estimate the distance from the Earth to Mars. Let's assume both planets are on the same side of the Sun. Consider the mean distance from the Sun to each planet as the radius of a circle. Use the mean distance you calculated from the Sun to Earth and the Sun to Mars to determine the estimated direct distance between the Earth and Mars. What if Earth and Mars were on opposite sides of the Sun, like this? These activities and more are located in the Educator's Lesson Guide, which can be downloaded from our NASA Connect website.
Why are we exploring Mars?
What tools and techniques does NASA use to explore Mars?
Why are we exploring Mars? Hey, that's a great question. Let's visit NASA's Jet Propulsion Laboratory in Pasadena, California, to learn more about America's commitment to Mars exploration.
NASA is committed to exploring Mars. In fact, they will be sending a robot to Mars once every 2 years for the next decade. Mars is very interesting because not only is it right next door, but it's the planet with the most hospitable climate in the solar system. So hospitable, in fact, that it may once have been the home to primitive bacteria-like life. These pictures show dried up river and lake beds, and so we know that liquid water flowed on the surface billions of years ago.
So where has all the water gone? Has it just floated off into space?
Scientists think that a lot of the water may be chemically bound to the soil, or underneath the surface in either liquid or ice form. Understanding where the water currently is can help us understand the history of water on Mars, which is important in determining if there is or ever was life on that planet.
Why do scientists suspect that there was once water on Mars?
What is the Mars microprobe and how will it navigate below the surface of Mars?
What is the relationship between geometry and the Mars microprobe?
Okay, guys, I'm here with Dr. Robert Mitchell-Tree, who is working on current explorations into the Martian landscape. Right now, we're on top of NASA Langley's Impact Dynamics Facility. Back in the 1960s, this is where they tested the lunar landers. Pretty cool. Dr. Mitchell-Tree, what on earth are we doing up here?
Well, I like it up here. You can look down on the surface of the Earth from up here. Like you can look out at the water and how it meanders across the land there. And we know that even if you remove that water, there would still be a distinctive shape to the pattern it makes. And it's those kind of patterns we see on the surface of Mars, but none of them have any water in them. And we wonder, where did the water go?
So where do scientists think the water went?
Well, some of them think it seeped beneath the surface. And that's the purpose of Mars microprobe, to go to Mars and look for water beneath the surface.
Is that the microprobe?
Well, this is just a model of the microprobe. The actual microprobe is much larger, about the size of a basketball. But it has this same shape. And it's this shape, it's actually like a right triangle that is used to fly through the atmosphere of Mars. As it approaches the planet, it'll be tumbling. And then when it hits the atmosphere, no matter how it hits the atmosphere, it'll reorient itself and fly nose forward. And it'll continue to fly like that all the way down, decelerating from 17,000 miles an hour to 400 miles per hour when it strikes the surface. This outer shell breaks away, and the inside penetrometer, that fist-shaped instrument, pierces down through the soil and begins looking for water underneath the surface.
So once the microprobe penetrates the surface, how does it find water or look for water?
Well, this really small fist-shaped instrument has a small drill in it, and when it's down in the dirt, it digs with the drill, pulling some dirt inside of it, and it has even a laser in there also, and it uses the laser to shine some energy on the dirt, and it measures the outgassing of the dirt, and that's how it looks for water.
Okay, big deal. So what if it finds water on Mars?
Water's the key to understanding several interesting aspects about Mars. We don't go there just to understand if there's water there, it's what effect water has on other things. The more interesting question is the question of life. All life we know on Earth is tied some way to liquid water. And if we can find water on Mars, we're one step closer to understanding if life ever existed there or still does.
Well, that's definitely something to think about. Thanks, Dr. Mitchell-Tree.
My pleasure.
Appreciate it. Hey, you, if you're interested in topics like life on Mars and other Mars explorations, just check out the website address on your screen. Speaking of the web, let's go on location to Virginia Beach, Virginia, with NASA's Educational Technology Program Manager, Dr. Shelley Canwright.
I'm here at Bayside High School in Virginia Beach, Virginia, where students from Bayside Middle School, along with their partner school, Brandon Middle School, have been involved in a quest as participants in the Mars Millennium Project, a national arts, sciences, and technology education initiative. Let's check in with the students to learn about their quest.
The Mars Millennium Project challenges teams across the nation to design a community for 100 people arriving on Mars in the year 2030. We have used this challenge to create an online activity to work on one aspect of building a Mars community, the development of a public relations campaign to gather public support for the Mars mission.
Our quest can be broken down into 5 simple steps. Step 1, reflection. Our teachers explained to us our mission. We divided ourselves into 4 groups: mission commanders, environmental specialists, natural resource engineers, and astronomy specialists. Each group had specific questions to research and think about. Step 2, imagine. We took the knowledge gained from our research to write a survey and then brainstormed how to use technology to conduct an electronic poll and to tabulate the results. In the process, we gained experience in the use of software for word processing and spreadsheets. Step 3, discover. The results of our electronic survey were analyzed. This information helped us see what were key issues to the public so we might address them in our advertising campaign. Step 4, create. We have now entered the design phase of our quest, where we are creating ads and sharing our presentations with our partner school using video conferencing technology. Step 5, share. Our final step will be to share with NASA and others our Mars advertising campaign in the form of a multimedia presentation that we will post on the NASA Connect website. Also, we will post our electronic survey for others to try and to make their own comparisons.
But Jennifer, if any of our viewers would like to learn more about the Mars Millennium Project, they should visit the NASA Connect website for a link to the Millennium website. And now, as a final incentive, registered submissions to the Mars Millennium Project received by June 1st, 2000 will be placed on a microchip for transfer to Mars on a future NASA mission. Now, how's that for connecting thousands of young people through technology and then using technology to take their plans for the future to another planet?
Thanks, Shelley, for all that cool cyberspace information. We'll definitely use it.
Well, that's about it for today.
Now, before we go, we've got lots of people to thank, especially the middle school students and teachers, the NASA researchers,
NASA Langley Research Center,
NASA Ames Research Center,
NASA's Jet Propulsion Laboratory,
Dr. Israel Tabak,
and Dr. Shelley Kenwright.
If you would like a videotaped copy of this NASA Connect show and the Educator's Guide lesson plans, contact CORE, the NASA Central Operation of Resources for Educators. All this information and more is located on the NASA Connect website. For the NASA Connect series, I'm Jennifer Pulley.
And I'm Van Hughes, and we'll see you next time
on NASA Connect. Bye. Bye.
Bye.
Oh, good thing I have on a hard hat. Ellipses and angles really aid in the navigation of spacecraft to Mars, like the Viking.
Tootin'.
How can we get more information on the Mars Microprobe?
Well, I recommend the kids go to the Mars Microprobe website.
A circle. A circle. You know, Pythagoras proved that there are... It's old meat now, Bill.